Hello, everybody. Now, welcome back to Math 1342. Today, we're going to talk about Chapter 5, Section 2, Binomial Distributions. In this section, we're going to look at three main parts. We're going to describe binomial distributions or binomial probability distributions. We're going to find probability values for a binomial distribution. We're going to calculate the mean, standard deviation, and variance for binomial distributions. Once we find those, then we'll use those to determine whether the values X are significantly high or low, or neither. So that's what we're going to do in this section. First off, let's look at the basics of binomial probability distributions. So what these do, binomial probability distributions allow us to deal with events that have outcomes that belong to only two categories that are binomial. Belong to only two categories. So that's what the whole binomial probability distribution thing's all about. So let's define it. Binomial probability distribution. It's a procedure whose results meet the following conditions. Or requirements. fixed number of trials. It can't go on forever. It has a fixed number of trials. Trials are independent meaning that one trial does not affect the outcome or the probability of the second or the others. Each trial must have all outcomes classified into exactly two categories. Has to be binomial, which means two. Typically, we look at pass, fail, on, off, success. So true, false, whatever. This has to be only two possibilities. And lastly, the probability of a success must be the same in all trials. So these are four conditions that have to. So you have to have a fixed number of trials. You can't keep on going forever and ever. The trials each have to be independent. The results of the trials have to result into one of two distinct outcomes, categories, and the probability of success must be the same for each trial. Here we have some notations. Then I'm going to show you the formula. Success and failure. The two outcomes have to be easily distinguishable. XY, TF, SF. So, or O, you can't use OO for on off. So you would plus minus. The probability which is the probability of success. The probability of failure has to be 1 minus the probability of success. This is equal to Q. So P is success, Q is failure. N number of trials. The number of successes. Success is in N trials. So it has to be between 0 and N. P is the probability of success in one of the N trials. And Q, same thing, but the probability of a failure in one of the N trials. And the probability of X. So the probability of getting exactly X successes in N trials. All right, so let's look at the first example. Focus, focus, focus. When an adult is randomly selected with replacement, remember, has to be independent, because if it was without replacement, then that one event changes the next event. So has to be with replacement. There is an 85% probability that this person knows what Twitter is based on a Pew Research Center survey. Suppose we want to find the probability that three of 5 randomly selected adults know what Twitter is. Does this procedure result in a binomial distribution? If this procedure does result in a binomial distribution, identify the values of N, X, P, and Q. So let's look at the first one. Does this procedure result in a binomial distribution? Remember, we have those 4 conditions. Finite number of trials, N equals 5 adults. So it is finite. We want the probability of exactly three adults who know what Twitter is. So is it independent? Yes, because one person answering doesn't affect the other person. So yes, there's no influence here whatsoever. Each event has only one of 2 possible outcomes. Yes, they know, or no, they don't know what Twitter is. for each adult, there is an 85% probability that they know what Twitter is. Therefore, there is a 15% probability that they don't. And those are the same for each subject. So yes, it is a binomial distribution. So B, we have to know N, X, P, and Q are. N, 5 adults. We want to know 3 of the adults. So this one is success equals 85%. That means failure, Q equals 1 minus P, which is 0.15. All right, let's go to the next topic. Treating dependent events as independent. So selecting a sample without replacement makes it a dependent event. So with that replacement is a dependent event. Remember, if you with that replacement, you keep the person, and then that makes the odds change for everybody after that. So that means automatically the event of the success of one person depends or influences that success on the others. But we can treat that event as if they were dependent or independent. by applying the 5% guideline. And here it is, the 5% guideline for cumbersome calculations. And it says, when sampling without replacement, and the sample size is no more than 5% of the population size, then we can treat the selection as being independent. Even though they are dependent. What we can is, if the sample size is large enough that 5% doesn't make much of a difference, then we can go ahead and treat it as independent, because it's making the changes so insignificantly small that it won't matter. So that's what the 5% rule. So in your homework and everything, if you're looking at, it gives you a population size, take 5% of that and see if the sample you're using is within that number. Three methods for finding binomial probabilities. Method 1. Calculating binomial probabilities using formulas. Using calculators or technology or software. Using tables. All right, so we're going to look at all three of these. It's best that you know how to use all three of these, because if you ever lose your calculator or don't have your computer with you, or whatever reason, you always know how to do it by calculating or using tables. All right, method 1. Formula driven. The binomial probability formula is this. The probability of x equals n factorial over n minus x factorial times x factorial. So that's the permutations times the probability of success raised to the power x. Q, probability of failure, is n minus x, where x is equal to numbers from 0 all the way to n, any of those numbers. Where n equals the number of trials, the number of successes, that's what x equals, in n trials. P is the probability of success in any one trial, and Q is just the opposite, the probability of failure in any one trial, 1 minus P. So that's how we figure it out. Actually, yeah, this another way you could look at this, because in statistics, this is the combination rule. N factorial over n minus x factorial, x factorial. Remember, n is as many you have, x is what you're looking for. So it's number that you have to minus over number that you don't want factorial times the numbers you do want factorial. So the probability of x is actually ncx times px qn minus x. Remember, success, how many successes do we have? N minus x, that's how many failures you have. All right, let's look at an example for this one. Given that there is a 0.85 probability that the randomly selected adults knows what Twitter is, use the binomial probability formula, which is n factorial, n minus x factorial, p of x, q n minus x. So we have to figure out what each of these are. Use the binomial probability formula to find the probability that when 5 adults were randomly selected, 3 no. So we're looking at no's. Because this is important, because what if we're looking at 3 people do not know? That would not be the success value, because this is when people know what it is. If it said do not know, we want the opposite of that, which is 0.15. So it's whatever the question is looking for. We want people who know, 85% people know, so that's how they go together. So we want 5 people total out of 5 adults. We want exactly 3. Possibility of success is 0.85. So 1 minus 0.85 is 0.15. This number here will always be an integer. So 5 factorial, 5 minus 3 factorial, 3 factorial, 0.85 times 3, that's what x is. So that's success. There were 3 successes. The failures, that's where you use n minus 3. 5 people total. We take away 3 successes. All we're left with is 2. Five minus 3 is 2 factorial. Five minus 3 is 2. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 0.85 cubed is 0.614125. 0.15 squared is 0.0225. So 321 cancels a 321. 2 cancels with a 4. So 5 times 2 is 10. Times 0.614125. 0.0225. Multiply those together. 3 significant digits, because these were 2 significant digits. We want 1 more than that, so we want 3. That's our final answer. So this is the probability of getting exactly 3 adults who know what Twitter is out of 5 adults selected. All right. So rule, very important. Don't round up. Whatever your calculator has, put these in as they are. Only round at the very end. Only round at the end. All right. Look at method 2. Calculator or software like Excel. You could use Excel for that also. Between 74 and 2011, 460, this is the chapter question, 460 NFL team games were decided in overtime, and 252 were won by the team that won the overtime coin toss. Is the result 252 wins in 460 games equivalent to random chance, or is 252 when significantly high? So what do we know here? Our N is 460. That's the main total we have. The probability of success and the probability of failure, a team winning or losing, is both 50%. Remember, 50% equals 0.50. Now, X, to find the true probability of all this, we have to go from 252 all the way to 460 and add them all together. So equals 209 times. Because there's 208 numbers from 252 to that, plus you have to count 252, so it's 209 times. So we wouldn't use a calculator for that. We can't use a table for that because it's just too many times to look through it. So for this, we'd have to use either a spreadsheet and calculate this stuff using a computer. And this is what the outcomes would look like. So our n is equal to 5. These are the probabilities. Our binomial distribution would give us these values. In StatDisk, number of trials is 5. Success is 0.85. So this calculation gives us the mean, deviation, and variance. You'd have, as StatDisk, it's free on your computer. I'll send you the link, but it's free on there. Usually looking at the tools for the class. I'll send you that shortly. And you can use Excel, calculating whatever we get there. Calculators got me there. I don't use calculators. So using StatDisk is your best bet. Just put in this information that we have, hit go, and it'll give us the rest. So we have to find the probability for each one of our outcomes. So, and this is only part of it. You notice the bar here, all that from top down, we'd get the solution. And so that is, it's a rare event rule, because you have so many different possibilities can happen. So you choose the method depending on which data set you have. number of repeated calculations over and over and over and over and over. All right. Let's see here. Oh, yes. What number was that one? Example 3, okay. Method 3, using a table. In our book, it's table 1A1 in Appendix A. So as long as your n is less than 8, less than equal to 8, you can use a chart. Here are the steps using a table. Step 1. Locate n and the desired corresponding value of x. When you find the n and corresponding, you'll have one row of numbers. Your value, the number you're looking for. Align the row with the desired probability of your success. Along the top. The corresponding value is the horizontal. This corresponding value represents desired probability and here's if the number is very small, like 0.00064, you'll get 0 plus. So this is what it would look like. Let's look at this. Devil of a problem. The Harris polls found that 6% of adults believe in the devil. Assuming that the randomly selected 5 adults So n equals 5. And the probability, if you're looking for people, how many adults? The probability that exactly 3 of the 5 believe in the devil. So we're looking for the first one is x3. This is for number 1. And for number 2 is the probability that the number of adults who believe in the devil is at least 2. At least 2. So it's 2, 3, 4, or 5. This is at least 2. So the only thing we don't want is 1. What we could do is take 1 minus the probability of 1, and that'll give us the same answer, as opposed to probability of 2, probability of 3, probability of 4, probability of 5. Finding each of those and adding them, we could just find out what we don't want, subtract it from 1, and then we have the answer. All right, so this is what we would look for. So we'd go to our table, table 1, A1. N is 5. X is 3. So we're looking at this one. And go all the way across. On the very top, you have 0.1 point. We want a 60%. So we want this column and this row. So the probability is 0.346. So the probability at exactly 3 is 0.346. All right, so, or we could look at this one. All right, the next one. Let's look at 1 minus the probability of 1 against this. So n is 5. We want the probability of 1 or 0 at 0.6. So it's 0.077, 0.10. So we add up those two together, we get 0.10 plus 0.77, 0.87. No, it's 0.0. So it's 0.087. So 1 minus 0.087 would make it 0.913. Or we could find the probability of getting 2, the probability of getting 3, the probability of getting a 4, or the probability of getting a 5 using the same chart. Probability of getting a 2 is 0.230. 0.230. Of getting a 3 is 0.346. 0.259 and 0.078. If we add up all those together, we get 0.913. And yeah, I'll send you guys a copy of that table. using mean and standard deviation for critical thinking. Binomial distributions are a special type of discrete probability. That's distribution. So we can find the mean, standard deviation, and variance using formulas. And they are. Since it's discrete, it's probably, we're looking at the population, it's n times p, number of elements you're looking total, times the probability of success. Standard deviation number you have, probability of success times probability of failure, the square root of that, because the variance is the square all right, so that's, now this is what we're going to be looking for in this category. Remember, okay, we also are going to use the range rule of thumb. Remember, those are used for significant high and significant low. Significant high if greater than mean plus 2 standard deviations. Significantly low if less than the mean minus 2 standard deviations. And not significant if between again, that's what we've been talking about all along. So let's get an example here. Example 3 involved n equals 4, that's overtime football games. So n equals 460. We get p is equal to 0.5, q is equal to 0.5. Okay, assuming that the winning overtime coin toss doesn't provide an advantage. So both teams have 50-50 chance. A, Find the mean and standard deviation for the number of wins in groups of 460 games. Remember, so we're dealing with populations, n times p. N is 460 times 0.5 is 230.0 games. So the average, the mean, is 230 games. The standard deviation is n times p times q. N times 460 times 0.5 times 0.5. 460 times 0.5 is 230. .230 times 0.5 is 115. So square root of 115, just a little bit bigger than 100 and just a little bigger than 100. So it's 10 point something, 10.7. So the standard deviation is that. Okay, now B. It says, use the range rule of thumb to find the values separating the numbers of wins that are significantly high or low. Significantly high equals mu plus 2 rho, which is 230 plus 2 times 10.7, 21.4, which is 251.4. That's significantly high. Anything greater than that. Significantly low is a mu minus 2 standard deviations. .230 minus 21.4 equals 208.6 games. So anything greater than or equal to that is significantly high. Anything less than or equal to that is significantly low. And C, is the result of 252 overtime wins in 460 games significantly high? .252 wins is significantly high because it's greater than or equal to 251.4, which is there. Right, so that covers that section. All right, we have one more in chapter 5 and we're done with it. Good luck.